What if I told you that right now, at this very moment, you are traveling through time at exactly 299,792,458 meters per second? Not through space, through time. And the reason you can't go faster is because you're already moving at maximum speed through the fabric of reality itself. Here's something that will absolutely shatter your understanding of existence. Time isn't something that just passes around you, like water flowing in a river. Time is something you're actively moving through, and the speed of light isn't just the universe's speed limit for moving through space. It's the speed limit for moving through space-time itself. You, me, everyone watching this video right now is traveling at light speed, always, every single moment of your life. The greatest physicist of the 20th century, Albert Einstein, discovered something in 1905 that would break reality as humanity understood it. He proved that time and space aren't separate things. They're woven together into a single fabric, and the speed of light is the cosmic constant that holds the entire structure together. But here's what will blow your mind. When you move faster through space, you move slower through time. Not metaphorically, literally, measurably, scientifically proven. This means that the speed of light doesn't just define time, it is the fundamental exchange rate between space and time. It's the conversion factor written into the source code of reality itself. Before we dive into this mind-bending journey that will fundamentally change how you perceive reality, do me a favor, hit that like button right now. This video took months of research to create, and we're about to spend the next 3 hours unraveling one of the deepest mysteries in physics. Subscribe to the channel and ring that notification bell so you don't miss the next exploration. And I'm curious, where in the world are you watching this from? And what time is it for you right now? Drop a comment with your country and local time. Let's see how many different moments in space-time we can connect through this single video. Are you watching from New York at midnight? Tokyo at noon? London during your morning coffee? Let me know. Now, let's begin the journey. Let's start with a question that seems simple, but isn't. What is time? You might say time is what clocks measure, but that just pushes the question back. What are clocks actually measuring? You might say time is the thing that keeps everything from happening at once, but that's circular reasoning. We define time by its effects, but we struggle to say what it actually is. Here's what ancient philosophers thought. Time is absolute. There's a universal clock ticking away somewhere in the cosmos, and everyone, everywhere, experiences the same moment simultaneously. If it's 12 o'clock noon for you, there's some objective sense in which it's really 12 o'clock noon everywhere in the universe, even if different time zones label it differently. Isaac Newton, writing in 1687 in his Principia Mathematica, stated it explicitly. Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external. In Newton's universe, time was like a river flowing at a constant rate, carrying all events along with it. Space was the stage, time was the universal clock, and they were completely separate things. This made perfect sense to everyone for over 200 years. It matched our everyday experience. If you and I synchronize our watches, and then you get on a plane and fly to the other side of the world, our watches stay synchronized. Time passes at the same rate for both of us. Except it doesn't. Think of it like this. Imagine the universe as a massive ocean, and you're swimming through it. You always thought you were swimming through space, moving from place to place, while time just happened to everyone equally, like the ocean's temperature being the same everywhere. But Einstein discovered that space and time are more like the ocean's depth and width. They're both dimensions of the same thing. And here's the kicker. You're not just swimming through space or through time. You're swimming through space-time, and you only have so much swimming speed to distribute between moving through space and moving through time. In 1887, two scientists named Albert Michelson and Edward Morley conducted what they thought would be a simple experiment. They wanted to measure how fast Earth was moving through the luminiferous ether, the substance that scientists believed filled all of space and carried light waves, like air carries sound waves. They built an incredibly precise instrument called an interferometer. The logic was simple. If Earth is moving through the ether, then light traveling in the direction of Earth's motion should move at a different speed than light traveling perpendicular to Earth's motion, just like how a boat moves faster downstream than across the current. They measured and measured and measured, and they found ... nothing. Zero difference. No matter which direction they measured, light always traveled at exactly the same speed, 299,792,458 meters per second. This was like discovering that no matter how fast your car is going, when you throw a ball forward, it always moves away from you at the same speed, whether you're parked or driving 100 miles per hour. It violated every intuition about how motion works. Scientists tried to explain it away. Maybe Earth drags the ether with it? Maybe the measuring equipment contracts in the direction of motion? The Dutch physicist Hendrik Lorentz even worked out mathematical equations in the 1890s, describing how objects would need to physically contract and how time would need to slow down to make the experimental results work. But he thought these were just mathematical tricks, not physical reality. Then came Einstein. In 1905, Albert Einstein was a 26-year-old patent clerk in Bern, Switzerland. He wasn't affiliated with any university. He didn't have access to fancy laboratories. He just had his mind, a pencil, and paper. And he asked a question that no one else had dared to take seriously. What if the Michelson-Morley result isn't a measurement error? What if light actually does travel at the same speed for everyone, no matter how fast they're moving? If you really accept this, truly accept it, then everything else has to change. Time, space, simultaneity, causality, everything. Here's why. Imagine you're standing on a train platform, and a train passes by at half the speed of light. Someone on the train shines a flashlight forward. You see that light beam traveling away from you at the speed of light. Let's call it c for short. But here's the impossible part. The person on the train also sees that same light beam traveling away from them at speed c, even though they're already moving at half the speed of light. In Newtonian physics, this is mathematically impossible. If you're moving forward at 50 miles per hour, and you throw a ball forward at 30 miles per hour, someone standing still sees the ball moving at 80 miles per hour. Velocities add. That's just common sense. But light doesn't work that way. Light always travels at c, no matter who measures it. This is the second postulate of Einstein's special theory of relativity, published in his paper on the electrodynamics of moving bodies. The only way this can work is if time itself runs at different rates for you and the person on the train. Not because of some mechanical effect on clocks, because time itself, the actual rate at which moments pass, is different. What if I told you that this isn't just theory? In 1971, physicists Joseph Haffel and Richard Keating took 4 atomic clocks, the most precise timekeeping devices humans had ever built, and flew them around the world on commercial airplanes. When they brought them back and compared them to identical atomic clocks that stayed on the ground, the traveling clocks had measured less time. Not by much, only a few hundred nanoseconds, but exactly the amount Einstein's equations predicted. Time had literally slowed down for the moving clocks. Stop and think about what this means. This isn't science fiction. This isn't a thought experiment. This is measured, verified, physical reality. If you live your entire life moving around driving cars, flying in planes, you will age slightly less than someone who stays perfectly still. The difference is tiny, but it's real. You are a time traveler. Every time you move, you're choosing to move a little slower through time. But here's what will really blow your mind. You can't avoid this trade-off. You are always moving through space-time at exactly the speed of light. Always. When you're sitting still in space, you're moving through time at maximum speed. When you move through space faster, you necessarily move through time slower. The total velocity through space-time remains constant, the speed of light. The physicist Brian Greene explains it with this perfect analogy. Think of it like a car that can only go 60 miles per hour total. If you're driving north at 60 miles per hour, you're not moving east or west at all. If you turn to go northeast, you're now going, say, 40 miles per hour north and 40 miles per hour east, but your total speed is still 60 miles per hour. In spacetime, you're always driving at light speed. When you're not moving through space, all 299,792,458 meters per second of your motion is through time. When you move through space, some of that motion gets diverted from the time direction to the space direction. This is why nothing with mass can reach the speed of light. If you were moving through space at the speed of light, you'd be using all your space-time velocity for spatial motion. There'd be no motion through time left. Time would stop completely for you. You'd be frozen in a single moment forever, from your perspective. And since you can't go slower than stopped through time, you can't go faster than light through space. Light itself, photons, do exactly this. They move through space at c, which means from a photon's perspective, no time passes at all. A photon emitted from a star billions of light years away experiences no time during its journey. From its reference frame, it's created and absorbed in the same instant, even if billions of years pass for us. We're going to dive much deeper into this, but I want you to pause and really absorb this. The speed of light is the speed at which everything, including you, moves through spacetime. It's not a speed limit in the traditional sense. It's the fundamental rate of motion through reality itself. Now, let's get to the heart of why the speed of light defines time. To do this, we need to understand what spacetime actually is. You're probably thinking of spacetime as space and time together, like two things combined. But that's not quite right. And this misunderstanding is what prevents most people from really getting relativity. Spacetime isn't space plus time. It's a single four-dimensional structure where 3 dimensions are spatial and 1 is temporal. But they're all part of the same geometric object. And the speed of light is the conversion factor between the spatial dimensions and the temporal dimension. Think of it like this. Imagine you have a map with distances measured in miles, but then someone hands you a time measurement in hours. You can't compare them directly. Miles and hours are different types of units. But if you know a specific speed, say 60 miles per hour, suddenly you can convert between them. 1 hour equals 60 miles at that speed. The speed acts as a conversion factor. The speed of light does exactly this for space and time. In the equations of relativity, time measurements are multiplied by c to convert them into spatial units. 1 second of time equals 299,792,458 meters of space at light speed. This isn't just mathematical bookkeeping. It reveals that space and time are measured in fundamentally the same units. They're both dimensions of the same thing. Hermann Minkowski, Einstein's former mathematics professor, figured this out in 1908. He declared, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski realized is that space-time has a geometry, just like space does. In ordinary space, you can measure the distance between 2 points using the Pythagorean theorem. Distance squared equals x squared plus y squared plus z squared. In space-time, there's an analogous measure called the space-time interval, but with a crucial difference. The temporal component has a negative sign. The space-time interval equals x squared plus y squared plus z squared minus c squared times t squared. That negative sign is everything. It's what makes space-time fundamentally different from ordinary four-dimensional space. And it's what creates all the weird effects of relativity. Here's where this gets visual and intuitive. Imagine every event in spacetime, every moment and location as a point. From your current position in spacetime, right now, wherever you are, there are certain events you could potentially reach in the future, and certain events that could have reached you from the past. If you imagine drawing all the possible paths that light could take from your current position into the future, they form a cone shape called your future light cone. Everything inside this cone is potentially reachable by you because you can travel at speeds less than light. Everything outside this cone is unreachable. You'd have to go faster than light to get there, which is impossible. Similarly, all the events in the past that could have influenced you, that could have sent light or any other signal that reaches you now form your past light cone. Here's what's profound. The surface of your light cone, the boundary itself, represents paths that light takes. And from the perspective of light itself, from a photon traveling on that surface, the space-time interval is zero. Not small, zero. For light, space and time perfectly cancel out. The spatial distance traveled exactly equals c times the temporal duration. So x squared plus y squared plus zcyt equals zero. This is why light travels at the speed it does. It's not really a speed in the traditional sense. It's the fundamental null interval of space-time geometry. Light moves along the boundary between past and future, between here and there, between cause and effect. The speed of light isn't a property of light. It's a property of space-time itself. What if I told you that the reason you can't send information faster than light has nothing to do with engineering limitations? It's not that we haven't built a fast enough spaceship or a powerful enough transmitter. It's that faster than light communication would literally be equivalent to sending messages backward in time. Here's why. Remember that simultaneity, the question of which events happen at the same time, is relative. Events that appear simultaneous to you might not be simultaneous to someone moving relative to you. Imagine you're on Earth and your friend is on Mars. You send a signal that travels faster than light, say, twice as fast. From your perspective, the signal travels through space, but not backward in time. You send it at noon. It arrives at 12:01. All is well. But now consider someone traveling very fast relative to both Earth and Mars. Due to relativity of simultaneity, from their perspective, the event of the signal being received on Mars might occur before the event of it being sent from Earth. To them, the signal is traveling backward in time. If this were possible, you could create causal loops effects that occur before their causes. You could send yourself a message telling you not to send the message. It creates logical paradoxes that suggest such signals are fundamentally impossible. The speed of light isn't just a speed limit. It's the cosmic censorship mechanism that protects causality itself. It's the universe's way of preventing paradoxes. And this is only necessary because time is relative, which is only true because the speed of light is the same for all observers. Every piece connects. The speed of light defines the geometry of spacetime, which makes time relative, which means the speed of light must be a universal limit to prevent causality violations, which reinforces that time cannot be absolute. It's a self-consistent structure, and the speed of light is the keystone holding it all together. Still with me? We're about to go deeper. Everything I've told you so far is just special relativity, the special case where we're only dealing with constant velocities. No acceleration, no gravity. But Einstein wasn't satisfied. He spent the next 10 years developing a more complete theory. And what he discovered was even more mind-bending. Gravity isn't a force pulling objects together. Gravity is the curvature of spacetime itself, caused by mass and energy. And once again, the speed of light is the key to understanding how this works. But before we get there, let me ask you something. Have you hit that like button yet? We're 1/5 of the way through this journey. And if you're finding this valuable, let me know by engaging with the video. And if you're watching this right now, Pause for a second and comment with your favorite science fact or mind-blowing realization. Let's build a community of curious minds. Now, let's talk about gravity and time. In 1907, Einstein had what he later called the happiest thought of my life. He was sitting in his chair at the patent office when he realized, if a person is falling freely, they don't feel their own weight. Think about it. If you're in an elevator and the cable snaps during the fall, you'd float relative to the elevator. You'd feel weightless, exactly like an astronaut in orbit. In fact, astronauts in the International Space Station aren't in zero-gravity Earths. Gravity is nearly as strong up there as on the surface. They feel weightless because they're in free fall, constantly falling around Earth. Einstein realized that this wasn't just a coincidence. There's no experiment you could do inside a sealed falling elevator to determine whether you're falling in a gravitational field or floating in deep space far from any masses. Gravity and acceleration are equivalent. This simple insight, called the equivalence principle, led Einstein to spend the next 8 years developing the general theory of relativity, published in 1915. And the conclusion was shocking. Gravity isn't a force at all. Massive objects don't pull on each other. Instead, mass and energy curve spacetime, and objects move along the straightest possible paths through this curved spacetime. But here's what's crucial. When spacetime curves, time and space don't curve equally. Gravity affects time more strongly than it affects space. Near a massive object, time runs slower, not just for clock's actual time, the flow of moments, the rate at which cause leads to effect. The physicist John Wheeler summarized general relativity with this perfect phrase: space-time tells matter how to move. Matter tells space-time how to curve. Let me give you a concrete example. GPS satellites orbit Earth at about 20,000 kilometers altitude. At that height, Earth's gravitational field is weaker than at the surface, so time runs faster on the satellites, about 45 microseconds per day faster. But the satellites are also moving at about 14,000 kilometers per hour relative to us on the surface. Due to special relativity time dilation from motion, time on the satellites runs slower, about 7 microseconds per day slower. The net effect: time on GPS satellites runs about 38 microseconds per day, faster than time on Earth's surface. This seems tiny, but GPS works by measuring the time it takes for signals to travel from satellites to your phone. Light travels 30 centimeters in 1 nanosecond. In 38 microseconds, light travels about 11 kilometers. If GPS didn't account for relativistic time dilation, your position would be off by several miles after just 1 day. Every time you use GPS, you're relying on Einstein's equations about how the speed of light defines time's flow in curved spacetime. Think of it like this. Imagine spacetime as a rubber sheet. When you place a massive object on it, the sheet sags. But it doesn't sag equally in all directions. The temporal dimension sags more than the spatial dimensions. An object sitting still in curved spacetime is actually moving through time, and the curvature redirects some of that temporal motion into spatial motion. It falls. This is why objects fall. Not because gravity pulls them, but because the curvature of spacetime naturally channels their motion through time into motion through space. Einstein's field equation, the one that describes how mass and energy curve, spacetime contains the speed of light in a crucial way. The equation is g equals 8g per c times t. Don't worry about what each symbol means. Just notice that c, the speed of light to the 4th power, appears in the denominator. This enormous number, about 810, is what makes gravity so weak compared to other forces. You need a massive amount of energy or mass to create noticeable spacetime curvature. But the deeper point is this: the speed of light appears directly in the equation that connects matter and energy to the geometry of spacetime. It's not just a conversion factor, it's the fundamental coupling constant that determines how much a given amount of mass energy will warp the fabric of time and space. E equals mc tells you how mass and energy are equivalent. The field equation tells you how that mass-energy curves spacetime. And c appears in both, because c is the exchange rate between mass and energy, between space and time, between geometry and matter. The speed of light is the fundamental proportionality, constant written into the structure of reality. Here's something that will absolutely blow your mind. Black holes. What is a black hole, really? It's a region where spacetime is curved so extremely that the future light cone of anything inside the event horizon points inward. Once you cross that boundary, every direction forward in time leads deeper into the black hole. Not because there's a force dragging you in, but because the geometry of spacetime itself has been warped so dramatically that forward in time literally means closer to the center. You can't escape a black hole for the same reason you can't travel backward in time. The direction out is in your past, and the speed of light, the maximum rate of motion through spacetime, prevents you from going there. At the event horizon itself, time dilation becomes infinite. If you could hover just above the event horizon, you can't, not without infinite energy, and you watched a clock falling in. You'd see the clock slow down and freeze as it approached the horizon, never quite crossing. From your perspective, it would take infinite time for anything to cross the event horizon. But from the perspective of someone falling in, they cross in finite time. They don't feel anything special at the moment of crossing. The event horizon isn't a physical surface. It's a point of no return defined by the geometry of spacetime. The physicist Kip Thorne worked out the mathematics of what you'd see if you fell into a black hole. As you approach the event horizon, you'd see the outside universe appear to speed up. The stars would whirl faster and faster. If you could survive long enough, you couldn't. You'd be torn apart by tidal forces. You'd see the entire future history of the universe play out before your eyes as you crossed the horizon, because time outside progresses infinitely fast relative to your time at the horizon. Black holes aren't just objects in space. They're structures in spacetime where time itself becomes so distorted that it trades roles with space. Inside the event horizon, the radial direction becomes time-like, and the time direction becomes space-like. Moving toward the center becomes as inevitable as moving forward in time is for us. Let's step back and look at the bigger picture. We've seen that the speed of light is constant for all observers. This means time is relative. Different observers measure different durations. Space and time form a unified spacetime with the speed of light as the conversion factor. Gravity curves spacetime, affecting time more than space. The speed of light appears in the fundamental equations describing all of this. But is the speed of light just one weird constant that happens to define time? Or is there something deeper? Some physicists believe time isn't fundamental at all, that time emerges from more basic structures, and the speed of light is part of what creates the illusion of time. In quantum mechanics, the Schrödinger equation describes how quantum states evolve. And guess what appears in that equation? A term that looks like time evolution, but the rate is set by Planck's constant divided by energy. For photons, particles of light, the energy is directly proportional to frequency, with the speed of light appearing in the proportionality. The physicist Carlo Rovelli has argued that time is not fundamental, but rather emerges from the quantum dynamics of matter and fields. In his view, what we call time is really just a way of organizing the correlations between different physical systems. The speed of light in this picture becomes the fundamental rate at which information can propagate, and time emerges from the structure of causal relationships. Think of it like this. Imagine reality as a massive computer simulation. Stay with me. This is just an analogy. The processor has a clock speed, a maximum rate at which it can update information. That's like the speed of light. Time, in this analogy, is what emerges when the simulation runs. It's not that the simulation exists in time, but rather that time is generated by the sequence of updates. Now, I'm not saying reality is actually a simulation, but this analogy captures something deep. The speed of light might be more fundamental than time itself. Time might be what we experience when information propagates at the maximum possible rate through a quantum substrate. We're about to dive into quantum mechanics and some truly bizarre implications. But first, I want to hear from you. In the comments, tell me, has this changed how you think about time? Do you find it comforting or unsettling that time is relative rather than absolute? Are you more fascinated by special relativity's time dilation or general relativity's gravitational effects on time? Also, we're almost an hour in. If you're still here, you're clearly someone who loves deep exploration of fundamental questions. Make sure you're subscribed, because we're going to do more videos like this on quantum mechanics, consciousness, the nature of reality, and other mind-bending topics. Now, let's talk about what happens when we combine relativity with quantum mechanics, because that's where things get really weird. Quantum mechanics, developed in the 1920s by physicists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac, describes the behavior of matter and energy at the smallest scales. And its deeply strange particles behave like waves. You can't measure position and momentum simultaneously with arbitrary precision. Systems exist in superpositions of multiple states until measured. But early quantum mechanics had a problem. It wasn't compatible with special relativity. Schrödinger's equation treated time and space differently. Time was a parameter, while position was unobservable. This asymmetry violated the spirit of relativity, which says time and space should be on equal footing. In 1928, Paul Dirac solved this problem. He developed an equation, now called the Dirac equation, that described electrons in a way fully consistent with special relativity. The speed of light appeared explicitly in his equation, naturally incorporating the relativistic relationship between energy and momentum. But Dirac's equation had a bizarre prediction. For every solution describing an electron, there was also a solution describing a particle with the same mass but opposite charge. Initially, people thought this was just a mathematical artifact. But in 1932, Carl Anderson discovered the positron antimatter counterpart of the electron in cosmic ray experiments. Antimatter isn't science fiction. It exists because the marriage of quantum mechanics and relativity requires it. When you insist that quantum mechanics respects the speed of light as a fundamental constant, antimatter falls out of the mathematics automatically. This led to the development of quantum field theory in the 1940s and 1950s. Pioneered by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga. In this framework, particles aren't really particles. They're excitations in quantum fields that permeate all of spacetime. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. And the speed of light? It's the maximum speed at which these ripples can propagate. It's built into the structure of the fields themselves. Here's where the speed of light becomes absolutely crucial for quantum mechanics. In quantum field theory, there's a principle called causality. Events separated by space-like intervals, events outside each other's light cones, cannot influence each other. If they could, you could create violations of causality, effects before causes. But quantum mechanics has this weird property called entanglement. Two particles can be correlated in ways that seem to involve instantaneous influences across space. Einstein famously called this spooky action at a distance and thought it proved quantum mechanics was incomplete. In 1964, physicist John Bell proved that Einstein was wrong. Quantum entanglement is real, and experiments have confirmed it thousands of times. If you measure one entangled particle, you instantly know something about the other, even if it's on the other side of the galaxy. But and this is crucial, quantum entanglement cannot be used to send information faster than light. You can't control what result you get when you measure your particle, so you can't encode a message in the measurement outcomes. The correlations are only visible when you compare results afterward, using slower than light communication. The speed of light saves causality. Quantum mechanics can have non-local correlations connections between distant events, but the speed of light ensures these correlations can't violate cause and effect. Think of it like this. Imagine two coins that are magically correlated. When you flip one and get heads, the other always shows tails, no matter how far apart they are. That's like entanglement weird correlations across space. But you can't control whether you get heads or tails when you flip your coin. So you can't use this correlation to send a message. You can only discover the correlation existed after the fact. The speed of light is what makes quantum mechanics weird, but not paradoxical. Now here's something that will really blow your mind. Remember how I said time might emerge from more fundamental structures? In quantum field theory, there's a deep connection between time and temperature. In the 1970s, Stephen Hawking discovered that black holes emit radiation. The event horizon isn't perfectly black. It glows very faintly with thermal radiation. This Hawking radiation comes from quantum effects near the event horizon. Virtual particle pairs pop into existence from the quantum vacuum, and sometimes one falls into the black hole while the other escapes. From far away, it looks like the black hole is emitting particles. But here's the kicker. The temperature of Hawking radiation is proportional to the surface gravity at the event horizon, divided by both the speed of light and Planck's constant. These fundamental constants, E and AA, appear together, linking gravity, quantum mechanics, and thermodynamics. The temperature is also inversely proportional to the black hole's mass. Larger black holes are colder. Smaller black holes are hotter. If you could make a tiny black hole the mass of a mountain, it would glow white-hot and evaporate in a burst of radiation. This suggests a profound connection between time, temperature, and the speed of light. Thermodynamics, the science of heat, and entropy, has an arrow of time. Heat flows from hot to cold. Entropy increases. You can't unscramble an egg. This arrow of time might be connected to the structure of spacetime itself, with the speed of light being the fundamental rate constant. Some theories suggest that time itself is a thermodynamic phenomenon, that what we experience as the flow of time is really the increase in entropy, and the speed of light sets the maximum rate at which entropy can increase, because it sets the maximum rate at which information can spread. Let's dig deeper into causality, the relationship between cause and effect, because this is where the speed of light's role in defining time becomes most clear. In classical Newtonian physics, causality was simple. If event A causes event B, then A happens before B, and everyone agrees on this ordering. Time was absolute, so the order of events was absolute. But in relativity, the order of events depends on your reference frame. Events that one observer sees as simultaneous, another observer might see as sequential. Does this mean cause and effect are relative too? The answer is no, but only because of the speed of light. Here's the key. If event A causes event B, then a signal must travel from A to B. That signal can't go faster than light. So B must be in A's future light cone, the region of spacetime that A can causally influence. For any two events where one is in the other's light cone called time-like separated events, all observers agree on their order. If I see A before B, everyone moving at any velocity will also see A before B. The speed of light makes the causal structure of spacetime invariant. Events that are space-like separated, outside each other's light cones, can't causally influence each other. And for these events, different observers can disagree about which happened first. But this doesn't create paradoxes because there's no causal connection. The physicist Roger Penrose developed beautiful diagrams called Penrose diagrams that map the entire causal structure of spacetime onto finite pictures. Black holes, expanding universes, and even hypothetical wormholes all have characteristic causal structures that are determined by how light cones are oriented. In the 1970s, physicist Jacob Bekenstein discovered something remarkable. Black holes have entropy. Entropy measures disorder, or more precisely, the number of possible microscopic states consistent with a macroscopic description. A black hole's entropy is proportional to the area of its event horizon, divided by the square of the Planck length, the smallest meaningful length scale in physics, about 10 meters. The Planck length is defined by a combination of fundamental constants. It equals the square root of ag per c cubed, where g is Newton's gravitational constant, a is Planck's constant, and c is the speed of light. Notice that c appears again. The speed of light is woven into the very fabric of what constitutes the smallest meaningful unit of space. But here's what's profound. If black holes have entropy, and entropy is related to information, then black holes contain information. In fact, they contain the maximum amount of information that can be stored in a given region of space. The information is encoded on the surface, the event horizon, not in the volume. This leads to a radical idea called the holographic principle, developed by Gerard 't Hooft and Leonard Susskind in the 1990s. The principle suggests that all the information contained in a volume of space can be encoded on the boundary of that region. Reality might be holographic, a three-dimensional projection of information encoded on a two-dimensional surface. And the speed of light? It's the maximum rate at which information can be transferred from one region of the holographic surface to another. Time, in this picture, is intimately connected to information flow, and the speed of light sets the fundamental rate of that flow. Think of it like watching a movie. The film contains a sequence of still images, but when played at the right speed, you perceive motion and the passage of time. The frame rate is like the speed of light. It's the rate at which information updates, creating the experience of temporal flow. We're about 80 minutes into this journey, and I want to shift gears a bit. We've covered a lot of abstract physics equations, theories, thought experiments. But what does all of this mean for you, personally? How should this knowledge change the way you experience your life? First, recognize that your intuition about time is wrong. Not just slightly off, but fundamentally mistaken. You experience time as something that flows uniformly, carrying you from past to future at a constant rate. But that's not what time is. Time is relative, flexible, inseparable from space. Every moment of your life is a point in four-dimensional space-time. And the present moment you're experiencing right now is not the same as anyone else's present moment. When you talk to someone on the phone across the country, you might think you're having a conversation at the same time. But due to relativity of simultaneity, there's no objective fact about whether they're speaking in your present, your past, or even your very near future. The difference is tiny fractions of a nanosecond, but it's real. There is no universal now. This might feel unsettling. We build our lives around the assumption that there's an objective present moment that we all share. We think about the past as fixed and the future as open. But relativity suggests that, in some sense, all moments in time exist equally. The past, present, and future are all out there in the block universe of space-time. This leads to one of the most philosophically challenging implications of relativity: eternalism, or the block universe view. If different observers disagree about which events are happening now, then now can't be a fundamental feature of reality. Instead, all of space-time past, present, and future exists simultaneously as a four-dimensional block. Your birth, your childhood, this moment reading this script, your death, all of it exists as a permanent structure in space-time. From this perspective, you're not a three-dimensional object moving through time. You're a four-dimensional object, a space-time worm, extending from your birth to your death. Think of it like a movie reel. All the frames exist simultaneously on the film. When you watch the movie, you experience the frames in sequence, creating the illusion of motion and time. But the entire movie past, present, and future is already there on the reel. This view is called eternalism, and it's suggested by the mathematics of relativity. Einstein himself seemed to believe it. When his lifelong friend Michel Besso died in 1955, Einstein wrote a letter to Besso's family saying, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. Only a stubbornly persistent illusion. Let that sink in. But here's the thing. Even if the block universe is the correct description of reality from a God's eye view, it doesn't change your experience. You still experience moments sequentially. You still have to make choices not knowing the outcome. You still feel like time flows. So why do we experience time as flowing if it's really a static four-dimensional structure? This is one of the deepest unsolved problems in physics and philosophy. It's called the problem of time's arrow, or the problem of the experience of temporal flow. There are several contributing factors. One is thermodynamics. Entropy increases toward the future, and our memories record the past, but not the future. This creates an asymmetry that makes the future feel different from the past. Another factor is consciousness itself. Your subjective experience of the present moment, what philosophers call qualia, is tied to neural processes in your brain that take time to occur. When you experience the present, you're actually experiencing a synthesis of information from the past few hundred milliseconds, assembled into what feels like a single moment. And here's where the speed of light comes back in. All the information processing in your brain neurons firing, neurotransmitters crossing synapses, is limited by the speed of light. Signals in your brain travel much slower than light, but ultimately, any information transfer is bounded by c. The rate at which you can update your model of reality is limited by this fundamental constant. Your experience of time passing might be, at its core, the experience of information propagating through your brain at finite speed, with the speed of light as the ultimate limiting factor. Think of it like this. Imagine you're a pattern of information encoded in a physical substrate, your brain. That pattern is constantly updating as new sensory information comes in and as internal processes occur. The rate of updating creates the subjective experience of time passing, and that rate is ultimately limited by how fast information can propagate, which is limited by the speed of light. In this view, the speed of light doesn't just define time in physics, it defines the rate at which you experience consciousness itself. Stop and think about what this means for your life. Every thought you're having right now, every sensation, every moment of awareness, it's all constrained by the fundamental structure of spacetime. The speed of light isn't just some abstract constant relevant only to physicists. It's built into the very fabric of your conscious experience. You are not separate from the universe, observing it from outside. You are a pattern in the universe observing itself, and the rules that govern stars and galaxies and black holes also govern the firing of neurons in your brain and the flow of your thoughts. Before we continue, I want to know, how does this make you feel? Does it make you feel insignificant, just a tiny pattern in a vast cosmos? Or does it make you feel connected, intimately woven into the fundamental structure of reality? Drop a comment and let me know. This community we're building isn't just about learning facts. It's about grappling with what these facts mean for how we see ourselves and our place in existence. And if you haven't already, hit that subscribe button. We're going to explore consciousness, quantum mechanics, the origin of the universe, and other profound questions in future videos. You don't want to miss it? Now let's tackle one of the ultimate questions. Did time have a beginning? And what role does the speed of light play in understanding the origin of the universe? In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding. If you run this expansion backward in time, everything gets closer together. Go back far enough, and all the matter and energy in the universe was concentrated in an extremely hot, dense state. This is the Big Bang, not an explosion in space, but an expansion of space itself. And it happened about 13.8 billion years ago, according to current measurements. But what does it mean to say time began at the Big Bang? This is where the speed of light becomes crucial again. In general relativity, space-time can have boundaries or edges, called singularities points, where the equations break down and quantities become infinite. The Big Bang is a singularity in the past, a boundary to space-time. Just as there's nothing south of the South Pole, there might be nothing before the Big Bang, not because something prevented earlier times from existing, but because before doesn't have meaning. Time itself began at the Big Bang. Physicists Stephen Hawking and Roger Penrose proved theorems in the 1960s showing that, given certain reasonable assumptions, singularities are inevitable in general relativity. You can't avoid them. If the universe is expanding and contains matter, then running time backward must lead to a singularity. Here's where the speed of light creates a puzzle. In the very early universe, in the first fraction of a second, after the Big Bang, the universe was incredibly hot and dense. Different regions of space were causally disconnected. They were so far apart that light hadn't had time to travel between them. Yet when we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that the temperature is the same in all directions to within 1 part in 100,000. How did regions that were never in causal contact all reach the same temperature? This is called the horizon problem, and it suggests that something strange happened in the early universe. The most popular solution is inflation, a theory proposed by Alan Guth in 1981. Inflation suggests that in the first tiny fraction of a second, around 10 seconds after the Big Bang, the universe expanded exponentially much faster than the speed of light. Wait, didn't I say nothing can go faster than light? That's true for objects moving through space, but space itself can expand at any rate. The speed limit applies to local motion through space, not to the expansion of space itself. During inflation, the universe doubled in size every 10 seconds or so. Regions that were initially close enough to be in causal contact were pushed apart faster than light could travel between them. This explains why the universe looks uniform. It all came from a tiny, causally connected region that was then stretched to cosmic scales. And what drove inflation? A hypothetical field called the inflaton field, with properties that caused space to expand exponentially. The details are still being worked out, but inflation solves several puzzles about the universe and makes predictions that have been confirmed by observations of the cosmic microwave background. Here's what will blow your mind. Inflation suggests that what we call the universe, all the galaxies we can see, everything within our observable horizon, might be just a tiny bubble in a vastly larger structure. During inflation, quantum fluctuations in the inflaton field got stretched to cosmic scales. Where the field decayed earlier, inflation stopped and the universe heated up, creating matter and radiation. That's what we see as the Big Bang. But in other regions, inflation might still be continuing, creating new bubble universes. This is called eternal inflation, and it leads to a multiverse, an infinite collection of bubble universes, each with potentially different physical laws and constants. In some bubbles, the speed of light might be different. In some, there might be extra dimensions of space. In some, the laws of physics might be so different that stars and planets and life couldn't form. We exist in a bubble where the speed of light happens to be 299,792,458 meters per second. In another bubble, it might be different, and time would flow differently. Causality would have a different structure, and any conscious beings there would have a totally different experience of reality. The speed of light in our universe defines time, but the speed of light itself might be just one possibility among an infinite variety realized across the multiverse. Everything I've told you so far comes from combining relativity and quantum mechanics. But there's a problem. These two theories don't fully fit together. General relativity describes gravity and spacetime geometry beautifully at large scales. Quantum mechanics describes matter and energy at small scales perfectly. But when you try to combine them to describe quantum effects of gravity or gravitational effects on quantum systems, the math breaks down. We need a theory of quantum gravity, and physicists have been working on this for decades. The two main approaches are string theory and loop quantum gravity, and both have profound implications for the nature of time. In string theory, particles aren't point-like objects, but tiny vibrating strings. Different vibration modes correspond to different particles. An electron is one vibration pattern. A photon is another. A graviton, the hypothetical quantum of gravity, is yet another. String theory requires extra dimensions of space, not just the 3 we experience, but 9 or 10 spatial dimensions total. The extra dimensions are curled up so small, we don't notice them. And the speed of light? In string theory, it emerges from the properties of these vibrating strings. It's not put in by hand. It comes out of the mathematics naturally. The fundamental length scale in string theory is the Planck length, about 10 meters, and the fundamental time scale is the Planck time, about 10 seconds, the time it takes light to travel 1 Planck length. At scales smaller than the Planck length and shorter than the Planck time, our usual notions of space and time break down. Quantum fluctuations in space-time geometry become so large that space and time as we know them cease to exist. There might be a foamy, chaotic structure at the smallest scales quantum foam, where space and time are radically different from our everyday experience. Loop quantum gravity takes a different approach. Instead of treating space-time as a smooth continuum, it proposes that space itself is made of discrete units quanta of space. Think of it like pixels on a screen. From far away, an image looks smooth and continuous, but zoom in enough, and you see individual pixels. In loop quantum gravity, space is woven from loops one-dimensional curves that interweave to form a network. The area of a surface and the volume of a region are quantized. They come in discrete units. And time might be quantized too. Instead of flowing smoothly, time might proceed in discrete ticks, like frames in a movie. The smallest meaningful unit of time would be the Planck time. Below this scale, the question, what happened earlier, might not have an answer. Time itself would be granular, not continuous. And what determines the Planck time? It's defined by fundamental constants. The Planck time equals the square root of GGC. Once again, a speed of light appears, this time to the 5th power. The speed of light, along with Planck's constant and Newton's gravitational constant, defines the smallest meaningful duration. If time is quantized, then the speed of light takes on a new meaning. It's not just the speed at which information propagates through spacetime. It's the fundamental rate at which spacetime itself updates from one quantum state to the next. Here's where things get really strange. In both string theory and loop quantum gravity, there's something called the problem of time. When you write down the fundamental equations of quantum gravity, time disappears. More precisely, the equations don't distinguish between time and space at the fundamental level. The entire history of the universe, all of spacetime, from beginning to end, is described by a single quantum state. There's no external time parameter. Change and evolution happen within the structure, but there's no overarching time in which the whole thing evolves. The physicist Carlo Rovelli describes this beautifully. Time is not fundamental, but emergent. At the deepest level of reality, there is no time. What we experience as time emerges when we look at the universe from within, focusing on particular variables and ignoring others. Think of it like this. Imagine a book. The entire story, every event from beginning to end, exists simultaneously in the complete book. There's no external time in which the book exists. The book just is. But when you read the book, you experience the story sequentially. Events seem to happen one after another. The flow of the narrative is real from your perspective as a reader, but it's not fundamental to the book itself. Reality might be like this. The entire history of the universe exists as a timeless quantum state, a mathematical structure. But when conscious beings emerge within that structure and interact with their environment, they experience a flow of time. And the rate of that flow is determined by how fast information can propagate, which is limited by the speed of light. What if I told you that the speed of light might not be truly constant? That it might have varied in the early universe, or might vary in extreme conditions? Some physicists have proposed theories where the speed of light was different in the past. John Moffat and João Maguiel developed varying speed of light theories in the 1990s as an alternative to inflation. If light traveled much faster in the early universe, that could solve the horizon problem without needing inflation. Other theories suggest that the speed of light might vary in extreme gravitational fields or at very high energies. If true, this would profoundly change our understanding of both relativity and quantum mechanics. But here's the thing. We've never observed any variation in the speed of light. Every measurement, from experiments on Earth to observations of light from distant quasars billions of light years away, shows the speed of light is constant to extremely high precision. If it varies at all, the variation is tiny. Still, the possibility remains open. And if the speed of light can vary, then the structure of time itself can vary. Time might flow differently under extreme conditions that we can't yet test. This is the frontier of physics, the edge of what we know, where possibilities open up and the foundations of reality become uncertain. We're over 2 hours into this journey, and if you're still here, you're amazing. We've traveled from the basics of special relativity to the cutting edge of quantum gravity. We've seen how the speed of light defines time and relativity, how it sets the maximum rate of information flow in quantum mechanics, and how it appears in the fundamental equations of physics at every level. But we're not done yet. In the final sections, I want to bring this all together to show you the big picture of how the speed of light, time, and reality are connected. And I want to explore what this means for the future, both the future of physics and your personal future. But first, let me ask, what's been your favorite mind-blowing moment so far? Was it learning that you're always traveling at the speed of light through space-time? That black holes turn time and space inside out? That time might not be fundamental at all? Let me know in the comments. And if you've made it this far, you deserve to be part of this community. Hit subscribe and turn on notifications so you're here for the next deep dive. Now, let's talk about the arrow of time and why the future is different from the past. All the laws of physics we've discussed, special relativity, general relativity, quantum mechanics, even quantum field theory, are time-symmetric. If you watch a video of fundamental particles interacting and then play it backward, the backward version shows processes that are also allowed by the laws of physics. Time has no preferred direction at the fundamental level. Yet our experience screams that time has a direction. We remember the past, not the future. Eggs break but don't spontaneously reassemble. Heat flows from hot to cold, not cold to hot. The universe evolves from the Big Bang toward increasing complexity and eventually heat death. Why? This is the mystery of time's arrow. The answer lies in thermodynamics, specifically the second law. Entropy always increases in isolated systems. Entropy is often described as disorder, but more precisely, it's the number of possible microscopic arrangements consistent with a macroscopic state. A broken egg has high entropy because there are many ways to arrange the molecules of a broken egg. An intact egg has lower entropy because there are fewer arrangements that give you a functioning egg. When the egg breaks, entropy increases, and the second law tells us this process naturally happens in one direction. But here's the puzzle. The microscopic laws of physics are time-symmetric, yet they give rise to the time-asymmetric second law. How? The answer is initial conditions. The universe started in an extremely low entropy state at the Big Bang. Why? We don't know. This is one of the deepest unsolved problems in cosmology. Given a low entropy initial condition, entropy will naturally increase over time, creating the arrow of time we experience. But this just pushes the question back. Why did the universe have such low entropy initially? Here's where the speed of light comes back in. Remember that the speed of light sets the maximum rate at which information can propagate. Entropy increase is fundamentally about information spreading about, microscopic details becoming scrambled and inaccessible. When you break an egg, information about the egg's initial state gets spread out among countless molecules, moving in random directions. To reverse this process, you'd need to know the exact position and velocity of every molecule and reverse them all simultaneously. The information is still there in principle, but it's become practically inaccessible. The speed of light limits how fast this information can spread. In a sense, the arrow of time, the rate at which entropy increases, is constrained by the speed at which information can propagate through spacetime. Think of it like ink diffusing in water. Drop ink into a glass of water, and it spreads out, increasing entropy. The rate of spreading is limited by how fast molecules can move. Similarly, entropy in the universe increases, and the maximum rate of increase is limited by the speed of light, the maximum speed at which any physical process can occur. This connects time's arrow to the speed of light in a fundamental way. The directionality of time, the fact that we experience past and future as different, is tied to entropy increase, which is tied to information spreading, which is limited by the speed of light. This connection becomes especially clear when we think about black holes. Remember Hawking radiation? Black holes evaporate by emitting thermal radiation, and eventually they disappear completely. But this creates a problem. What happens to the information about everything that fell into the black hole? If you throw an encyclopedia into a black hole, and the black hole eventually evaporates into featureless thermal radiation, where did the information in the encyclopedia go? In quantum mechanics, information is never truly destroyed. It's scrambled, but in principle, it's recoverable. But black hole evaporation seemed to destroy information, violating this principle. This is called the black hole information paradox, and it puzzled physicists for decades. Stephen Hawking initially thought information was destroyed, but in 2004, he changed his mind. Recent work in string theory and quantum gravity suggests that information is encoded in the Hawking radiation in subtle ways. It's scrambled extremely thoroughly, but not destroyed. The resolution of this paradox involves the speed of light in a crucial way. Information falling into a black hole gets scrambled as it crosses the event horizon, but it's eventually emitted in the Hawking radiation. The process takes lots of time for large black holes, and the speed at which information can be extracted is limited by the speed of light and the black hole's temperature. The speed of light, once again, governs the rate at which information can flow, even in the most extreme environments in the universe. Let's get practical for a moment. How do we actually measure time, and how does the speed of light relate to this? For most of human history, time was measured by astronomical cycles, the rotation of Earth, days, the orbit of the moon, months, the orbit of Earth around the sun, years. But these aren't perfectly regular, and they're not precise enough for modern technology. In 1967, the scientific community redefined the second based on atomic physics. A second is now defined as exactly 9,192,631,770 cycles of radiation, corresponding to the transition between two energy levels of a cesium-133 atom. This gives us atomic clocks that are accurate to better than 1 second in 100 million years. But here's what's interesting. In 2018, the International System of Units redefined several base units, including the meter. The meter is now defined as the distance light travels in 1/299th, 792,458 of a second. Read that again. The meter is defined in terms of the second and the speed of light. The speed of light is now an exact defined constant. C equals 299,792,458 meters per second. Exactly, by definition. This means that distance and time are no longer independently defined quantities. They're linked through the speed of light. This is deeply appropriate, given that relativity tells us space and time are part of a unified spacetime, with the speed of light as the conversion factor. The most precise clocks ever built are optical lattice clocks, developed in the 2000s and 2010s. These use lasers to trap atoms in a lattice pattern and measure the frequency of light they emit. The best optical clocks are accurate to better than 1 second in 15 billion years, longer than the age of the universe. These clocks are so precise that they can detect the time dilation predicted by relativity at everyday scales. If you raise an optical clock by just 1 centimeter about the width of your finger, it will tick measurably faster because it's slightly farther from Earth's center and experiencing weaker gravity. Researchers led by physicist John D. et al. In Colorado have used optical clocks to measure time dilation over height differences of just 33 centimeters. This isn't a thought experiment or an approximation. It's a direct measurement of how gravity affects time at scales you can experience in your daily life. Every time you climb stairs, you're moving into a region where time flows faster. The difference is tiny, about 1 part in 10, but it's real and measurable. The speed of light appears in the equations that predict these effects. Without knowing C with extreme precision, we couldn't predict or measure these tiny time dilations. The speed of light is the key that unlocks our ability to measure time with extraordinary accuracy. What does the future hold for our understanding of time and the speed of light? There are several exciting possibilities. First, quantum clocks. Researchers are developing clocks based on quantum entanglement that might be even more precise than optical lattice clocks. These could test relativity and quantum mechanics with unprecedented accuracy, potentially revealing tiny deviations from current theory that could point toward quantum gravity. Second, gravitational wave detectors. LIGO detected gravitational waves for the first time in 2015, opening a new window on the universe. Gravitational waves are ripples in spacetime itself, and they travel at exactly the speed of light. By detecting these waves from colliding black holes and neutron stars, we can test general relativity in extreme conditions and possibly find hints of quantum gravity effects. Third, new physics at high energies. The Large Hadron Collider and future particle accelerators might discover new particles or forces that change our understanding of spacetime. Some theories predict that space and time might have a more complex structure at extremely high energies, and the speed of light might emerge from some deeper principle. Fourth, tests of the speed of light's constancy. Astronomers are using observations of distant quasars and gamma-ray bursts to test whether the speed of light has changed over cosmic history. So far, they've found no variation, but the search continues with ever greater precision. Let's address the question everyone wants to know. Is time travel possible? Forward time travel is absolutely possible. We've already discussed it. If you move fast enough or sit near enough to a strong gravitational field, time will pass more slowly for you than for someone else. When you return, less time has passed for you. You've traveled into their future. In fact, astronauts on the International Space Station experience this. They're moving fast relative to Earth and in slightly weaker gravity, and the effects almost cancel out, but not quite. After 6 months in space, an astronaut has aged about 0.007 seconds less than someone on Earth. They've traveled 0.007 seconds into Earth's future. If you could get on a spaceship and accelerate to 99.999% of the speed of light, travel for 1 year by your clock, and return, decades would have passed on Earth. You'd emerge into Earth's future. This is real. allowed by the laws of physics, and only limited by our engineering capabilities. Backward time travel going into the past is much more problematic. General relativity does allow solutions where closed time-like curves exist paths through spacetime that loop back to your own past. These require exotic conditions like rotating black holes, Kerr black holes, traversable wormholes, or infinite cylinders of spinning matter, Tipler cylinders. But all of these have problems. Wormholes, if they can exist at all, probably require exotic matter with negative energy density to keep them open. Rotating black holes have unstable inner regions. And practical time machines would probably be destroyed by quantum effects. A time machine would amplify random quantum fluctuations until they become large enough to destroy the machine. The physicist Stephen Hawking proposed a chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel to the past, even if general relativity allows it mathematically. The speed of light, once again, is part of the protection mechanism. Causal loops would require faster than light travel, or extreme spacetime curvature, both of which are forbidden or unstable. Here's the final mind-blowing realization I want to leave you with. You are living in a moment that has never existed before in the history of the universe, and will never exist again. The specific configuration of atoms in your brain, the exact pattern of neural firing that constitutes your consciousness right now, the particular thoughts you're thinking this precise moment is unique. The arrow of time ensures that the universe is constantly evolving into new states that have never existed before. And the rate at which this happens, the rate at which new moments come into being, is governed by the speed of light. Information propagates at light speed. Change happens at rates limited by light speed. And your conscious experience updates at a rate ultimately bounded by light speed. You are not just in time. You are a process in time. Every atom in your body is vibrating. Every neuron is firing. Every cell is metabolizing. And all of this activity is orchestrated by the fundamental laws of physics, with the speed of light setting the tempo. The same speed that limits how fast galaxies can recede from each other, that determines how black holes swallow matter, that sets the maximum rate of quantum entanglement. That same constant is woven into every moment of your existence. Let's bring everything together. What have we learned about how the speed of light defines time? First, the speed of light is constant for all observers, which forces us to accept that time is relative. There's no absolute time flows at different rates for different observers, depending on their motion and gravitational environment. Second, space and time form a unified spacetime, and the speed of light is the fundamental conversion factor between spatial and temporal measurements. It's not just a speed limit, it's the exchange rate between different dimensions of reality. Third, the speed of light appears in all the fundamental equations of physics: special relativity, general relativity, quantum mechanics, quantum field theory, thermodynamics. It's not a coincidence. The speed of light is woven into the mathematical structure of reality itself. Fourth, the speed of light sets the maximum rate at which information can propagate, which means it sets the maximum rate at which cause can lead to effect, which means it defines the causal structure of spacetime, which means it defines what we mean by time. Fifth, at the deepest level in quantum gravity, time might not be fundamental at all. It might emerge from more basic structures, and the speed of light might be part of what generates the appearance of time from a timeless quantum reality. And finally, the speed of light connects to consciousness itself. Your experience of time passing, of moments flowing one into the next, is ultimately constrained by how fast information can propagate in physical systems, including your brain. The speed of light doesn't just define time. In a very real sense, the speed of light is time, or at least, it's the fundamental rate constant that determines how time works. So what does this mean for you? It means you're part of something magnificent. You're not separate from the cosmos, observing from outside. You're woven into the fundamental structure of space-time itself. The same laws that govern the motion of galaxies govern the thoughts in your head. The same constants that determine how black holes form determine how your neurons fire. This isn't a diminishment of your significance. It's an elevation. You are the universe experiencing itself. You are a way for the cosmos to know itself. Every moment of awareness you have is the universe being conscious of its own existence. And here's the empowering part. You have agency within this structure. Yes, the laws of physics constrain what's possible. Yes, the speed of light limits how fast you can process information and how quickly you can affect distant events. But within those constraints, you have freedom. The future is not predetermined by the past, despite the block universe picture. Quantum mechanics introduces genuine randomness into the evolution of systems. And even in a deterministic universe, chaotic systems, including brains, are so sensitive to initial conditions that they're effectively unpredictable. Your choices matter. Your actions shape the future, even if that future already exists from a certain perspective. You are navigating through space-time, always moving forward in time, always constrained by the speed of light, but always free to choose your path within those constraints. We're approaching the end of this journey, but before we close, I want to hear from you one more time. Has this changed your perspective on time? On reality? On your own life? Do you see time differently now? When you look at a clock, do you think about the fact that it's measuring your motion through the temporal dimension of space-time? When you move, do you realize you're trading spatial motion for temporal motion? Drop a comment and share your thoughts. This community is about more than just watching videos. It's about exploring the deepest questions together. Let me take you on one final journey through space and time to tie everything together with a cosmic perspective. Right now, as you're experiencing this moment, photons from the sun are taking 8 minutes and 20 seconds to reach Earth. This means when you see the sun, you're actually seeing where it was 8 minutes ago. You're looking into the past, not because of any technological trick, but because the speed of light is finite. Look at the stars at night. Alpha Centauri, the nearest star system, is 4.37 light-years away. When you see its light, you're seeing what was happening there over 4 years ago. The light left that star before you started watching this video, traveled through the void of space at 299,792,458 meters per second, and finally entered your eye. Some of the stars you see are hundreds or thousands of light years away. The Andromeda Galaxy, the nearest major galaxy to our own, is 2.5 million light years distant. The light you see from Andromeda left that galaxy when our earliest human ancestors were just beginning to walk upright on the plains of Africa. The farthest objects we can see are nearly 13.8 billion light years away. We're seeing them as they were just a few 100 million years after the Big Bang. We're literally looking back through time, watching the universe when it was young. And here's something profound. There's a limit to how far we can see, and it's determined by the speed of light and the age of the universe. The observable universe is a sphere around us with a radius of about 46 billion light years. Wait, how can we see things 46 billion light years away if the universe is only 13.8 billion years old, and light can only travel so fast? The answer is that space itself has been expanding. Light that was emitted 13.8 billion years ago from a region that was relatively close to us has been traveling toward us all that time, but the space between us was expanding as the light traveled. That region is now 46 billion light years away, even though the light has only been traveling for 13.8 billion years. The edge of the observable universe is called the cosmic horizon, and it's fundamentally defined by the speed of light. Beyond this horizon are regions of space that are receding from us faster than light, not because they're moving through space faster than light, but because the space between us is expanding so rapidly. These regions are permanently beyond our reach. We can never see them, never travel there, never receive signals from them. The speed of light has drawn a fundamental boundary around the portion of the universe we can ever observe or influence. Now think about this. Every conscious being in the universe has their own observable universe, their own cosmic horizon, their own now. An alien civilization in the Andromeda galaxy, if such exists, has a different present moment than we do. Events that are in our past might be in their future, depending on our relative motion. There's no cosmic consciousness experiencing all events simultaneously. Instead, the universe contains countless localized perspectives, each with their own experience of the present moment, all bound together by the causal structure defined by the speed of light. This is both humbling and extraordinary. You are one perspective among countless others, but your perspective is unique. No one else in the entire universe experiences precisely the same now that you're experiencing right now. Your present moment is yours alone. What about the far future? What will happen to time as the universe evolves? Current evidence suggests the universe will continue expanding forever. Dark energy, a mysterious force causing the expansion to accelerate, will drive galaxies apart. Eventually, in trillions of years, the expansion will become so extreme that galaxies beyond our local group will recede faster than light. They'll disappear beyond our cosmic horizon, one by one. Stars will exhaust their fuel. New stars will stop forming as gas is used up. The universe will grow dark and cold. Black holes will be the last major structures, and even they will evaporate via Hawking radiation over timescales of 10 to 10. Years numbers so vast, they're nearly incomprehensible. Eventually, the universe might reach a state called heat-death maximum entropy, where no organized structures exist, no energy differences remain, and nothing happens. Time, in a sense, would stop not because space-time ends, but because there would be no change, no events, nothing to distinguish one moment from the next. But here's the remarkable thing. We don't know if this is the true fate. There might be quantum fluctuations that create new universes. There might be cyclic processes we don't understand. The laws of physics might change in ways we can't predict. We're still learning. Consider your life against this cosmic backdrop. The universe has existed for 13.8 billion years. It will likely exist for trillions or quadrillions of years into the future. Your lifetime, maybe 80 or 90 years, is an infinitesimal flicker. But that flicker matters. In this brief moment, matter has organized itself into a form capable of understanding the universe. Atoms forged in the hearts of dying stars have assembled into a brain that can comprehend relativity, quantum mechanics, space-time, and the speed of light. You are a way for the universe to know itself, and you exist in an incredibly special time. You live in an era when stars still shine, when galaxies are visible in the night sky, when life and consciousness are possible. Trillions of years from now, the universe will be a dark, empty, cold place where nothing like your existence could occur. Right now, in this cosmological moment, the universe is at a perfect stage for conscious beings to exist and understand their origin and fate. You're alive in this sweet spot, the brief window when the universe is old enough to have created complex structures, but young enough that energy still flows and change still happens. And every moment of your existence is connected to the fundamental structure of reality through the speed of light. When you see a sunrise, you're watching photons that left the sun 8 minutes ago, traveled through the vacuum of space at the cosmic speed limit, passed through Earth's atmosphere, and entered your eyes, triggering chemical reactions in your retina that generate electrical signals that travel along your optic nerve into your brain, where they're processed into the experience of seeing. Every step of this process, from the emission of light to its travel through space, to its absorption in your eye, to the neural processing in your brain, is governed by the laws of physics, with the speed of light setting the fundamental rate. You are not separate from the universe. You are a pattern in the universe, intimately connected to every other part through the causal structure defined by the speed of light. The atoms in your body were created in stars. The energy powering your cells comes from the sun. The structure of spacetime determines how time flows for you. Everything is connected. Everything is one unified whole, and the speed of light is part of the glue holding it all together. But let's not lose sight of the practical significance either. Understanding how the speed of light defines time isn't just philosophical. It has real-world applications that affect your daily life. GPS navigation depends on relativistic corrections for time dilation. The internet relies on fiber optic cables carrying light-speed signals. Radio and television transmit information at light speed. Your smartphone's processor operates with clock speeds measured in gigahertz billions of cycles per second, pushing against the fundamental limits imposed by the speed of light. Future technologies will push these limits even further. Quantum computers might exploit quantum entanglement to perform certain calculations faster than classical computers, though still bounded by light-speed causality. Space exploration will always be constrained by light-speed communication delays. A message to Mars takes 4 to 24 minutes one way, depending on the planet's positions. If we ever develop interstellar travel, the relativistic effects we've discussed will become critically important. A spaceship traveling at 99% of the speed of light could reach Alpha Centauri in about 4.4 years as measured by Earth clocks, but only 0.6 years would pass for the crew due to time dilation. They could journey to distant stars and return to find centuries or millennia have passed on Earth. These aren't science fiction fantasies. They're mathematical consequences of special relativity, as real and certain as gravity. Throughout this journey, we've encountered questions that remain unanswered. Why does the universe have the structure it does, with 3 spatial dimensions and 1 temporal dimension? Why is the speed of light exactly 299,792,458 meters per second and not some other value? Why did the universe begin in such a low entropy state? These questions push at the boundaries of physics and philosophy. Some might have answers we'll discover through future research. Others might be fundamentally unanswerable. They might involve initial conditions or selection, effects from a multiverse that we can never directly observe. But the fact that we can ask these questions is itself remarkable. You, a pattern of matter organized by 13.8 billion years of cosmic evolution, can contemplate the fundamental structure of reality. You can ask why the universe is the way it is. You can grasp, at least partially, the mathematical laws governing spacetime. This is what consciousness gives you, the ability to step back from your immediate experience and understand the deeper patterns. You're not just living in the universe, you're comprehending it. Every moment of awareness you have is precious beyond measure. You exist in a narrow window of cosmic time when understanding is possible. You have access to knowledge that no human possessed just a few generations ago. You can comprehend ideas that would have seemed like magic to your ancestors. The fact that the speed of light defines time, this knowledge, transforms how you can perceive your existence. You're not floating in absolute time, carried along by some external current. You're navigating through space-time, a 4-dimensional structure where past, present, and future are all part of one geometric whole. Your consciousness rides along your world line, the path you trace through space-time from birth to death. And at each point, you experience a now that's unique to your reference frame, determined by your position and motion in this vast 4-dimensional landscape. This moment right now, as you engage with these ideas, is your present. It's the point where your world line intersects with the current state of your environment. And the rate at which new now moments come into being is determined by how fast information can propagate, which is limited by the speed of light. Here's the empowering message I want to leave you with. You can choose how you relate to time. Yes, the physics is fixed. The speed of light is constant. Time dilation effects follow strict mathematical laws. The arrow of time points from low entropy to high entropy. But within this structure, you have freedom. You can choose to live mindfully in each moment, recognizing that this present instant is all you ever truly have. You can choose to use your finite time in ways that matter to you. You can choose to pursue understanding, to create beauty, to connect with others, to reduce suffering, to increase joy. The fact that time is relative doesn't make your experiences less real. The fact that the block universe might contain your entire life from beginning to end doesn't mean your choices don't matter. The fact that you're subject to the laws of physics doesn't diminish your agency. You are a conscious pattern in the universe, bound by physical law, but free within those bounds to shape your path. The speed of light limits how fast you can process information and how far you can reach, but it doesn't dictate what you choose to do with the time you have. Despite everything science has learned about time and the speed of light, mysteries remain. Deep, profound mysteries that might take centuries more to unravel, or might never be fully resolved. Why does time have an arrow at all? Why did the universe begin in a low entropy state? Is time truly fundamental, or does it emerge from something more basic? Can the laws of physics be derived from first principles, or are they just brute facts about our universe? What is consciousness really? How does subjective experience arise from physical processes? Why do we experience time as flowing, moment by moment, when the mathematics suggests all moments exist equally? These questions remain open, and that's beautiful. It means there's still wonder to be found, still discoveries to be made, still mysteries to contemplate. The physicist John Wheeler said, "We live on an island surrounded by a sea of ignorance." As our island of knowledge grows, so does the shore of our ignorance. The more we learn, the more we realize how much we don't know. But that's not discouraging, it's exciting. It means the universe is endlessly fascinating, that there are always new frontiers to explore, new questions to ask, new understanding to seek. As we approach the end of this 3-hour journey, I want you to take a moment quite literally and just be present. Notice your breathing. Feel the passage of time as seconds tick by. Recognize that this moment, right now, is unique in the entire history of the universe. The exact configuration of particles that constitutes your brain and body right now has never existed before and will never exist again. You are a temporary pattern, a brief eddy in the flow of matter and energy through spacetime. And yet, in this brief existence, you can understand the cosmos. You can grasp the relationship between the speed of light and time. You can hold the entire universe in your mind, at least conceptually. That's a gift. Perhaps the greatest gift the universe offers? The ability to know itself through conscious beings like you. So use it well. Let this knowledge enrich your experience. When you look at the stars tonight, remember that you're seeing into the past. When you check your GPS, remember that it works because we understand time dilation. When you experience the passage of time, remember that you're traveling through space-time at the speed of light, always and inevitably. You are connected to everything. The speed of light is woven into every moment of your existence. Time is not something that happens to you. It's something you're actively participating in, a dimension you're moving through, shaped by the fundamental constants of physics. We've covered an enormous amount of ground in these 180 minutes. We started with the shocking revelation that you're always traveling at the speed of light through spacetime. We explored special relativity, general relativity, quantum mechanics, quantum gravity, black holes, the Big Bang, and the ultimate fate of the universe. We've seen how the speed of light appears in every fundamental equation, how it defines the causal structure of spacetime, how it sets the maximum rate of information flow, and how it might be intimately connected to the emergence of time itself. But more than that, we've connected these abstract ideas to your personal experience. You're not just learning physics, you're gaining a new perspective on your own existence. You're seeing yourself as part of the cosmic story, connected to everything from the smallest quantum fluctuations to the largest structures in the universe. So what do you do with this knowledge? That's up to you. Maybe it inspires you to learn more, to study physics or mathematics or philosophy. Maybe it changes how you experience each moment, bringing more awareness and presence to your daily life. Maybe it gives you a sense of connection to something larger than yourself. Whatever you take from this, I hope it's been worth your time. And speaking of time, thank you for spending 3 hours with me on this journey. The fact that you've made it to the end tells me you're someone who values deep understanding, who's willing to wrestle with difficult ideas, who finds meaning in exploring the fundamental nature of reality. If you haven't already, please hit that like button. It really helps this video reach more people who are curious about these profound questions. Subscribe to the channel and turn on notifications so you don't miss future deep dives into consciousness, quantum mechanics, the nature of reality, and other mind-bending topics. And please, share this video with someone who would appreciate it. These ideas are too important to keep to yourself. The more people who understand how reality really works, how time is relative, how space and time are unified, how the speed of light defines the structure of existence, the better equipped we are as a species to navigate our future. Here's my final thought for you. The universe is stranger and more wonderful than most people imagine. The mundane experience of time passing, of space existing, of being conscious, these are all manifestations of deep physical principles that we're only beginning to understand. You don't just live in the universe. You are the universe, temporarily organized into a form that can know itself. The atoms in your body were forged in stellar furnaces. The energy powering your thoughts comes from ancient sunlight. The structure of space-time determines how your moments unfold. And the speed of light, that constant we've explored so thoroughly, is woven into every aspect of your existence. It's the tempo at which reality unfolds, the maximum speed of causality, the conversion factor between space and time, perhaps even the rate at which consciousness itself operates. Does the speed of light define time itself? After 3 hours of exploration, I hope you can see that the answer is yes, but it's a subtle, profound yes. The speed of light doesn't just set a limit on how fast things can move. It's the fundamental constant that determines the structure of space-time, the flow of information, the relationship between cause and effect, and the very nature of temporal experience. Time is not absolute. Time is not separate from space. Time is not something external that flows around you. Time is a dimension of space-time, inseparable from the 3 spatial dimensions, with the speed of light as the fundamental constant linking them together. You are always moving through space-time at exactly the speed of light. When you're still in space, you're moving rapidly through time. When you move through space, you slow down through time. The total velocity through space-time remains constant. This is reality. This is how the universe actually works. And you, yes, you're living proof of these principles in action. Before I let you go, one last request. Leave a comment telling me what you're taking away from this journey. What was the most mind-blowing moment for you? What questions do you still have? What topics would you like to see explored in future videos? Let's build a community of people who care about these deep questions, who aren't satisfied with surface-level explanations, who want to understand reality at the most fundamental level. And remember, every time you look at a clock, you're measuring your motion through the temporal dimension of space-time. Every time you see light, you're witnessing the maximum speed of causality in action. Every time you experience a moment, you're participating in the mysterious emergence of consciousness from physical processes governed by the speed of light. You're not separate from these cosmic principles. You are these principles, temporarily organized into conscious form. Thank you for joining me on this journey through space, time, and the speed of light. Thank you for your curiosity, your attention, and your willingness to grapple with difficult ideas. Keep questioning, keep learning, keep wondering. The universe is vast, and strange and beautiful, and you're a part of it. Until next time, remember, you're traveling through space-time at the speed of light, right now and always. Make it count. This has been an exploration of how the speed of light defines time itself. If you made it this far, you're extraordinary. Hit that subscribe button, and I'll see you in the next deep dive into the mysteries of existence.